I guess we're probably going to get started. As is always the case with the last session of the day, it's far too much fun networking and having chats out there, and I hope you've all been having fun. To a large extent, I have. I would argue that getting this talk ready was less of the fun part, and I'll tell you why. I've given this as a workshop a number of times. Has anybody ever been to that workshop? Good, because you're going to get thoroughly bored. No. So the NDC crew said to me, look, you've submitted this workshop and we like it, but we'd really love for you to give this as a talk instead. And I thought, challenge accepted. Now, the thing is with speaking is you need to find words. The thing is with workshops is that I like to get people in a room and actually get their hands on the code and really dive into it and feel what they're doing. And we're going to be going through some concepts today that I'd really like you to be coding so you can actually see it happening. There's the magic of making it happen that you don't get when you're watching a talk. So to the largest extent possible, I hope I've managed to bring the life of what would be a workshop into this talk. If not, I apologize in advance. So, who is this clown standing in front of you at the moment? If you haven't met me before, even if you have met me before, I've been coding since I was 12. I have been breaking software since I was 15. My mum and dad both regularly used to break our Windows machine at home. This is in the days of Windows 3.1 and DOS 2 point something, I don't even know what. So I actually wrote tools to stop them breaking Windows. I've been advocating for security and privacy since I was 18, and not long after that I started running tech events. I managed to set my hair on fire at a tech festival when I was 40, so things seem to be going downhill. If you want to find out more about that, you can tweet me or you can... What's that one called? You can blue sky me. Is blue sky a noun yet? Should be. You can sky me at ben.sc. Also, I work, I don't know if you saw Phil's talk earlier today, he and I both work at Sonar. Sonar is basically a company that helps you write more clean, more quality code. We've got a number of tools like an IDE plugin that's totally free and open source that'll show you where you're writing really complex code, and if you do that, then the next developer who looks at your code is going to hate you. So don't make people hate you, write clean code, try out the Sonar products, they're great. But this talk is nothing about that, so I'll move swiftly along. So what I want to do is I want to have a chat. Not with you. I mean, I do. While you're here, let's have a chat. It's all good. If you have any questions at any point, by the way, just raise your hand and shout at me. But I want to have a chat with people online. I want to send a message to Alice and for Alice to be able to reply to me. And I want Alice to be able to reply to me in her own window. So I thought, let's write a chat app. Fairly simple, fairly straightforward. The problem is that in most situations, and somebody was saying to me, do you remember ICQ, do you remember Messenger, all those things? Most of these aren't very secure. Whoever controls the database of the chat can read the database of the chat. So this is not just an example, it's an actual screenshot of that conversation at the start of what would be the workshop. And you can see there, Ben sent Alice a message, and you can see what the messages are. So whoever has access to this database, and this isn't just going to be the database administrator, or somebody was talking earlier about access control and how people get trusted. It's like, oh no, Michael, he's fine. I trust him to have full admin rights to the database. But the problem is that it's never the people that you trust that you need to be worried about. It's the fact that their credentials can get compromised, or maybe they are the recipient of a phishing attack and they accidentally open access to systems. So Michael, yes, he's trustworthy, but he clicked on that email. Michael. So there are going to be a whole lot of people who could potentially get access to this. And let's say, for example, we don't want that. So we want to implement some kind of end-to-end encryption. So being the developer I am, I thought, you know what, I'm going to ask ChatGPT to use DALL-E to generate an image to help you all understand exactly what end-to-end encryption is about. So I said, draw a diagram that describes how end-to-end encryption works. Can you imagine how well this went? So unless you have any questions, that's the end of the talk. I'll put this up again at the end, just for fun. All right, so here's how end-to-end encryption actually works. We've got Alice and we've got Bob. Has anybody here ever looked into any kind of crypto stuff? Cryptography, not crypto, the other one that we don't want to talk about. There's Alice and Bob. Alice and Bob are the traditional characters that you have in encryption where Alice wants to send Bob a message. So we have Alice and Bob. Not sure about Bob, he looks dodgy. But anyway, Alice wants to send a message. She wants to say hi. So she sends it to the server, and the server stores the word hi, which then Bob can read by accessing that from the database. But the problem we have now is that a third party can come along and grab a laptop of some sort and plug it in and hack it in. Usually this character would be called Carol or Charlie. However, in this case, this is Phil Nash. Phil Nash is going to come along, he's going to hack the system, he's now reading our messages, and we don't want Phil to know because we're planning a secret surprise tonight. We're going to do karaoke, but don't tell him. For those of you who don't know, Phil's running the karaoke tonight, so stick around for that. All right, so what are we going to do? We're going to generate a public and a private key pair. And this is what we call asymmetric encryption, in that symmetric encryption is basically like, I want to encrypt this data with this passphrase. Now I have to tell you the passphrase and you can decrypt it. The problem is, how do I get that passphrase to you in a secure manner? If we can meet face to face, then sure, but if I email it to you, who has access to your email? It gets tricky. Asymmetric encryption allows me to generate a public key and a private key, for you to generate a public key and a private key, and as the name suggests, you can then share your public key with everyone. You have to keep the private key private. So we have the yellow key there, that's the public key, and then we've got the shield, the locked one, that's the private key, that's the one we're not going to share around. But Alice can send her private key to Bob, and Bob can send public key. I'm going to do this, by the way. I always get confused in my head between public and private when I'm actually talking. Alice sends her public key to Bob, and Bob sends his public key to Alice. And now Alice can actually grab the public key that Bob has just provided and use that to encrypt the message. So this is now encrypted with just Bob's public key. Now she can still decrypt it with her private key. But also, once this now goes to the server, it's encrypted data, can't really decrypt it. Charlie, or Phil, has now lost access to this. It's now an encrypted data blob, and there's nothing to see. There is plenty to see, but you can't decipher it without one of the private keys that was used to encrypt the data in the first place. So now when Bob gets the message to his client, his device, whatever he's using to read this chat, he gets this encrypted bit of data, which now he can't read either, but he can use his private key and use that to decrypt the message again and get the original message back. Clear as mud? Cool. Now, the advantage with this is you can actually do this multiple ways. You can have multiple private keys that are used to encrypt a single message. And then any of those public key, you can use multiple public keys to encrypt a single message. And then any of the private keys associated with those public keys will be able to decrypt the message. It's like those security things you've probably seen the memes of at, like when you go to a boatyard, or you've got access to a shared yard in the complex where you live. You'll have a chain of padlocks locking something together. Any one padlock that's unlocked can break that chain. Hopefully they'll lock it up again. As opposed to having, like, in parallel, 20 padlocks where all of them need to be unlocked. So in this case, you only need one of the private keys to unlock the message. So, next thing we would be looking at right now is tools for asymmetric encryption. Has anybody here implemented asymmetric encryption or any kind of encryption in their tools? Cool, a little bit. So, I won't ask you for names then, I'll just bring this up. Here are a handful, not all of them, but a handful of popular modules or libraries for cryptography itself, not necessarily a particular implementation or protocol, but cryptography itself. You'll see there are three here, NetPGP, OpenPGP, and OpenPGP PHP. Oh, and GNU PG. These are all protocols or implementations of a form of cryptography called PGP, or Pretty Good Privacy. GNU PG was the open source re-implementation of PGP. And all of these other ones that I just mentioned use PGP, which is a way of encrypting, and traditionally was used for encrypting emails. So if you've ever had systems in the past where you can upload your PGP key to encrypt messages, if anybody here uses ProtonMail, for example, that will automatically create, in fact, ProtonMail uses OpenPGP.js to generate public-private keys and to encrypt messages and to share those around. So these are all particular implementations. The others, Bouncy Castle, PyCryptodome, these are implementations of cryptography libraries. They don't actually do PGP themselves, but you could use them to implement PGP. I'm a strong proponent of never rolling your own crypto, so I would probably say let's not do that in this particular case. So let's get rid of those, because we're not actually going to implement them. GNU PG while it is a PGP implementation, is not actually a library, but it can be used directly by things like C or anything that can communicate via a system connection to underlying applications sitting on the computer that you're running your application on. So we're basically left with 3. In fact, the astute amongst you will realize that I've actually dimmed out a whole different set of 3. These 3 are the ones that actually work in web. So in this particular case, we've got a web chat. NetPGP is not going to help you with a JavaScript application. If you had a backend, then sure, use one of the others if you've got a backend service that's doing the encryption for you, but we're actually going to be doing the encryption in the browser. Some of you might be thinking, was that a good idea? The answer is no, and yes, and maybe, and we'll come to that as well. The browser obviously being an untrustworthy device within the ecosystem of your application because you have no idea what's running on it. So we've got these 3 options. Lipsodium is actually a C library, but if you use WebAssembly, you can use Lipsodium from within your browser, and that's kind of a cool option. Web Crypto API and Subtle Crypto are actually the crypto things that are built into the browser. They're not quite as easy to deal with when it comes to OpenPGP-based encryption, whereas OpenPGP.js, as the name suggests, is JavaScript library that will actually do OpenPGP. Now, there's no reason why you couldn't choose to use something like the Web Crypto API and encrypt the data and send that around that way. The reason why I chose OpenPGP is because it is pretty much a standard for communications encryption. And if you wanted to, in the future, allow another system, another client, for example, to interact with your data or to distribute, federate the system, having a standard that is well known and has been around for 30-something years, I'm pretty sure it's been around since the 80s, is probably the better way to go. So we're going to go with OpenPGP.js in this particular case. Not to say the others aren't going to do what you want, but for this, because it's a React application and it's in the browser, we're going to use OpenPGP.js. So we're going to use this to encrypt all the messages that are in the system. So in order to do that, there are a number of steps we need to take. The first thing we need to do is generate a key pair for everybody who's using the application. Now, OpenPGP.js will allow you to do that, and we'll have a look at some of the code. In order to make sure that the demo fails do not fail me, don't worry. It's just going to be code in slides, but we'll step through the important parts of how we implement this and how it then provides all the functionality that we need. But the first step is to generate a key pair. And for every user, you're going to need a public-private key pair, and they are generated together because they are intrinsically linked to each other. You have to use the public key to encrypt things for the private key to decrypt. So we do that. Then we need to store the keys somewhere, and this is a touchy subject when it comes to the web. But we'll discuss a little bit about where's good and where's bad and why that is and how we can mitigate issues and risks. In order to encrypt the message, remember, we needed all the public keys, so we're going to need to find a way of getting all of those public keys from all the people in the chat room. And then once we've got all those keys, we can encrypt the message with all the public keys we just retrieved. Can anybody spot a logic error in doing this every time somebody logs in? Or has any other questions?
Is it like 7 messages? Or is it 1 message with 7 potential keys?
So the question was, is it 7 messages or 1 message with 7 potential keys? Great question. It's actually going to be 1 message, 1 payload, but it's encrypted using all those 7 keys at the same time. So that 1 message, and we'll see an example of what the actual PGP encrypted message looks like, but that 1 message can be decrypted with any of the private keys. But it's still a single message.
Is it computationally heavy?
Is it computationally heavy? I mean, yes, because we're encrypting. How will it scale? So that's awesome. So if you wanted to do this for a chat room with 1,000 people, that's obviously going to be a higher cost of scale, the amount of computation that's required to do that. To be honest, nowadays, computers are actually pretty fast. When this stuff's running in the browser, browsers are pretty efficient at running JavaScript and getting this done. I wouldn't be too worried. If you're looking at millions of recipients for 1 message, then maybe it's time to re-architect and find a different way of encrypting things. In that case, what you could do is actually use symmetric encryption to use a known passphrase for encrypting and decrypting, which is much faster. And then you encrypt the passphrase with the public keys. And then you only have to decrypt the passphrase, which is a much smaller, like that'd be 40, 60 characters, whatever you wanted to use as a secure passphrase. Nobody actually needs to know that. You just randomly generate it, you encrypt the data, you asymmetrically encrypt the passphrase, you store both. So there are ways of improving performance, for sure. Yes?
I think one of the challenges is that if I give you key via a third party, I don't know whether you have received my private key or one that they create. Sorry, my public key or one that they create.
That's a very good point. So if you were to give me your public key via a third party, then there's no way for me to know that it's actually your public key. In that situation, there's two sides to that answer. First of all, we'll know very quickly if it's the wrong public key because you will not be able to read the message because it's not associated with your private key. But there is now somebody else whose key I do have. That's true. Now, what normally happens with PGP or any kind of public-private key, public key sharing mechanism, has anybody ever been to a PGP key signing session? No? I'm showing my age. So this happened quite a lot in the early 2000s where you would actually physically meet up with people and you would share a piece of paper with them and you'd have some ID and somebody would look at the ID and they'd look at you and they'd say, yep, that matches. And then they would say, is this your public key? And you'd say, yes, it is. And then I would initial it. So I know that I've cited it and I've seen the ID and the ID back. So then I would go home and I would get onto my laptop and I would pull down, basically because it's associated with an email address, I would pull down the key for your email address and I'd find the one that matches and I would painstakingly check every single character. In later versions, I could actually copy and paste. How you copy and paste from a piece of paper in the year 2000? It's a very interesting question. But there are ways of doing that. Now, because it is associated with email addresses, you can actually have public key stores. This is very common in the identity space, where you want to grab a key from an identity provider in order to verify that the JSON Web Token you've received is actually signed by that. And you would go to the provider's website to a .well-known address and grab the key that way. And there are similar ways of doing that. So there are ways of doing it. Now, if I was to accept your public key from you, then that's my problem for not verifying it's yours as well. So there's still a human element to this. I would always want to make sure that I get your public key from you, whatever mechanism that is. And that would still be fine by email. You could email me your public key. And in fact, if you're already using public-private key encryption for your email, then your public key is actually sent with most emails because it's part of the signature as well, because your emails will be signed even if they're not encrypted. But that's probably another whole hour's talk. So, any other questions before I move on? I'm liking this. Excellent. Okay, cool. So we're going to encrypt the message with all the public keys. We'll get one encrypted message back, and we'll store that in the database. However, next time I log in, it's going to generate a new public-private key pair for me, which we don't want. So let's first of all check to see whether I have a public-private key pair already. So that's the first step. If I've already logged in once before, I'm going to have that. So if I don't have it, then if I do, then I can skip the storing the keys part and all the rest of it and go straight to encrypting the message and sending it back to the server. But then, of course, I've got to decrypt the message as well. So we're going to decrypt the private key. Private keys generally have a passphrase associated with them, so you'd have to provide the passphrase in order to decrypt it. So this is essentially, it's not symmetric encryption per se, but it is that single passphrase, like that is a secret you have to keep. In essence, it's almost like the key is something you have and the passphrase is something you know. So it's almost, you probably get away with saying it's multi-factor. I don't know. You can create private keys without a passphrase. Don't. That's all I have to say on that matter. It does make it harder for the end user now, because now they're going to have, and there's going to be a QR code soon, so you can actually type messages into an actual chat. But you can have a username and password, your credentials for getting into the chat system to identify yourself. But then you've also got to have a passphrase for unlocking your private key. And how you message that and the user experience of that can be tricky, because now I've got two passwords that I've got to remember, and one that I have to keep very secret. So now that I've got decrypted the private key, I can actually load messages from the server, which are all ideally encrypted, and then I can use my private key to decrypt all the messages that have been encrypted with my public key. There's a message in there that has not been encrypted with my public key. Maybe it's because I wasn't a member of the chat when it was sent. Then I won't be able to decrypt that one. So you get a little bit of assurance that somebody jumps into the chat can't read all messages. But maybe you want them to, and we'll look at that too. So let's talk about storing keys. Can anybody suggest good ideas and bad ideas? where would you store a key in a web application? Give me the bad ideas first. Let's get cookies. Yes, perfect. Definitely storing them in cookies. Local storage. Yes. There's a few of them. In the URL. Oh, I don't have that one. I'm going to have to add that one in. Perfect. I like it. The advantage with storing with the URL is then you can bookmark it, and then you can come straight back in. You never have to provide your passphrase again. I like it. Perfect. There are some up here that just obviously aren't going to work for a web application. Hardware security modules, I think you can kind of do that through some kind of way. But I mean, we're going to get rid of cookies and local storage for starters, because I think everybody agrees that's a really bad idea, right? All you need is a malicious browser add-on or a cross-site scripting attack to get access to those fairly readily. There aren't any perfect places to store it, I'll let you know now, but those are definitely the worst. The next ones we're going to get rid of is on disk and operating key chain and key store, mainly because that's not something you really have access to in a web application. There is no server disk. You could create an API to store it, but now you're sending that to your API, and now you've got this sensitive data in transit, and ideally we don't want that. The hardware security module, there is actually, I don't know if the project's complete or just underway at the moment, but there is a project ongoing at the moment to link Tink, which is, I can't remember, it's a C module for connecting to the hardware module, to provide that through WASM to JavaScript, so that technically you could have a hardware module plugged into a server somewhere, ideally one that you trust, and essentially you're kind of making an API call to a hardware module to retrieve a key, but that's all sorts of complicated, and it doesn't actually solve the problem of getting the key into a browser environment. You still have to store it somewhere then, right? Unless you're making that call every time, it's still going to be in memory somehow at that point. So I'm going to get rid of that one. Too complicated, no real benefits to it. Web crypto would be a really cool one. It would be a really cool one. The only problem is that it itself is a form of crypto. You can store keys in web crypto, but only the keys that are generated by web crypto. We're generating our own keys. What you could do is you could take the private key, and then you can use the web crypto API in the browser to encrypt the web crypto key to store in the web crypto data store. And I think you can probably all agree that that's about as ridiculous as using the HSM module through WASM, in that it doesn't actually provide us that much more, because we're still going to be pulling it out at some point. Which leaves us with cloud key management services and databases, which to a certain extent, once you're looking at a front-end web application, are the same. Because either way, you're going to have to connect to them somehow and provide them some kind of credentials to say, give me the key. Cloud key management services are going to be more secure. But at the end of the day, it's still the same mechanism from a front-end application. Again, back-end application will be different. Yes?
So the user would authenticate, we authorize, and then the application would make a back-end API call, like the cloud key management service, and you have like protection on your transit to overcome like distaste of other transit methods.
Yes. So to rephrase, not to rephrase, to repeat, I don't know, it's not going to be the same words. The user authenticates and then does some kind of API call to a backend based on that authentication to retrieve the key. And in fact, I'm 2 clicks behind, so we're on database. In fact, there's an alternative option to this, in that most identity providers will actually allow you to store arbitrary data against the user, which is kind of like a database, right? So what you could even do is, depending on the identity provider you're using, is you can allow a user to log in, create an account, and then that identity provider will provide a JSON Web Token back to you, which you would normally use to make that API call. But what if that JSON Web Token already contained the public and private keys? Now, you are trusting the identity provider now to store those public-private keys, but to a certain extent, I would say that that's probably a more sane solution than a regular database provider, because their entire core purpose is to store and secure identities and credentials. So I would probably trust that maybe 0.2% more. There's a hand up at the back. If our threat model includes cross-site scripting attacks, aren't we stuffed no matter what we do? Yes. So if you're actually going to be doing this, I would recommend, rather than doing it in a web application, and web applications are really easy ways of doing workshops, right? Because you get your hands on the code. I'm not saying that the solution here is 100% perfect, but I would argue that it's probably like 98, 99% perfect. It depends on how much of a target you are. If it's just for you and your friends, sure, take this and run with it. If you're not actually that worried about what happens if somebody gets my keys, for an experimentation and learning about cryptography, if you wanted to be hyper secure and you are basically trying to communicate with a large entity that has the power and resources to really target you, then absolutely go for a secure backend model where the keys are kept on a server and not in a runtime environment running in an insecure application on somebody else's computer. Absolutely. Again, risk calculations are always an interesting question when it comes to security. But the principle would remain. The only thing you would gain by moving it out of the web application and into a server-based application is securing the keys better. But the way that you encrypt, the practices of encrypting for multiple people, key generation, all of those things would still be exactly the same. It's just hosted on a different machine. Hosted on a machine that you have more trust in. But again, I would argue, depending on where that machine is that you have trust in, who has access to that? If you really are worried about let's say it's a country-level entity that is really trying to target you, you think they're not going to be able to get access to that machine? This is where the fear, uncertainty, and doubt comes in. All right, so we're going to store it in a database. In this case, we're going to store it in the metadata of the user that comes back. So the first thing we want to do is check to see if the user's got a key pair. So quite simply, I'm sure most of you can follow this. If the user doesn't have user metadata in there, which is where this particular identity provider stores extra information that you want to about a particular user, if it doesn't exist, then we're going to return. This is basically a loop in your React. Anybody here not do React? So basically, let's call this an event loop. It's not really, but essentially this code is running. Anytime some of the variables change, it's going to rerun this. So when the user is not logged in, this isn't going to exist, and it's going to say, okay, well, let's not do anything. We're exiting early, basically. It's not that there's a failure, it's just we're exiting early. Once the user is authenticated, and there is a user object, and there is a user metadata element in the user array, or the object, and that has keys, then we're going to return those keys, or store those keys in state, essentially, in memory, and return. So now we have the keys from the user. So this is, to your point, the first point of concern that we have. It's stored in memory. There's still a possibility that there's going to be some kind of malicious code running through cross-site scripting or through a malicious add-on in the browser that's going to be able to iterate through the whole memory dump, basically, and say, find me something that looks like a key. It's a lot harder, though, than just iterating through cookies or local storage. So we're making it harder. It's the Swiss cheese model, right? Every layer makes you a little bit more secure. Once we have the keys, or maybe we don't have the keys, we're going to try and get a passphrase from the user. So there's a bit of JSX. Basically, if we don't have the passphrase yet, we're going to ask them for the passphrase, and we're going to set that again in memory. So now we have a private key stored in memory and a passphrase stored in memory. And I'm quivering a little more, but again, it's an example. So let's say we do have the passphrase, but we don't have any keys. We're going to start generating them. So that happens elsewhere, but we're just going to display some text saying generating keys so the user doesn't get confused. And then once we have the keys, we're going to start loading the messages and display them to the user. And in order to be able to decrypt those, we pass the keys through. That'll be the public and the private key, and the passphrase, so that we can actually use the private key to decrypt the messages that come back from the server. So how do we generate the key pair? There's a function called generate keys. It takes a nickname and the email. So the most identity providers, when you get a JSON response, if you're not familiar with JSON, it's basic with JSON Web Tokens rather. It's basically a payload in JSON that describes the entity that's logged in. It has a whole lot of claims about this person. The claim might be that my nickname is Ben and my email is ben@dechrai.com. Of course, we have the passphrase already. So we're basically going to pass these into the generate keys function so that we can generate, again, because PGP keys are based on email addresses. We're going to generate those. In order to generate those, we're basically going to use the OpenPGP function from the Yeah, function from the OpenPGP module. We're going to pass those in. That's copy and paste from their website, so don't worry about that too much. But it's really rudimentary and simple to get this working. Once we have those keys, we're going to save them. So set keys, we're going to save them into state in memory, but we're also going to call this endpoint. In this particular case, we're using Netlify, so I've got a Netlify endpoint. What it actually does is it talks to the identity provider, because there's an API secret between the two. We don't want that in the browser. So we've got an API endpoint that connects to the identity provider and says, hey, take for this user ID with this subject, store the access token and store the keys. Sorry, use this access token for authentication to store the keys as the data. So now the identity provider has my public and private keys for however comfortable that makes you feel. Grimacing up here. Phil's excited because he's the one trying to access our messages. He's like, I know exactly where I'm going first. Yeah. All right, so checkpoint. This is where we're at the moment. We've discovered whether a user has keys already. We've decided that in the case that they haven't, we're going to generate the key pair and store them. Next thing is retrieving other people's keys. So in this particular case, as well as storing public-private keys in with the identity provider, that save keys was also pushing just the public keys into the database, whose name I've just forgotten, Superbase. So we're storing that in there. So now we have a collection of all public keys in Superbase. We can make this call here from Superbase, select star from keys. Who here has used Superbase before? Who here has used any kind of REST-based database? Anything up here scare you yet? There's no authentication on this. Say again? Must be Firebase. No, it's Superbase. Public keys don't need to be stored securely, so we're okay. Thank you. So we're going to go to Superbase and say, give me all your keys, and then we're going to call the encrypt message with public key function, which we will have a look at now. There it is. Which basically takes a message and armored public keys. So in PGP parlance, I guess, keys are armored, which means that they are in such a format that they can be stored without risk of same kind of thing as if you're base 64, you're all encoding a piece of text to stick in a database or to send to an API endpoint. It basically armors those to make it easier to transport around, because usually they're binary, so it creates the text version. Or actually, I think it's the other way around. They are the binary version, and you need the text version. My brain is farting. Too late in the day. Anyway, so it's in a format that is not usually used. In order to use those keys, the read key is used. It takes that and it pushes that into the public keys array. So now we have an array of public keys that we can actually use to encrypt the data. There's no passphrase stuff going on here because they're the public keys. So then what we do is call the OpenPGP encrypt. We pass in the message itself that we want to encrypt and then the array of all the public keys that we're going to use to encrypt it. So again, to your point, single message goes in, single message comes out. And then we return that. It is all abstracted away. We don't need to care about it anymore. So we can now use that one function to encrypt the message and also the sender. So encrypting both parts. And this plays into a little bit of plausible deniability. If somebody does get access to the database, you could argue that maybe it's okay to store the names in plain text and then just encrypt the actual messages, but I would argue that names are also sensitive information, because they could actually identify you. Bob could be any Bob in the world, but if the identifier was an email address, then that specifically implicates somebody in taking part in a conversation. Whatever that conversation is, we don't know, but we know they were part of it. So we're going to encrypt both. So here's where we're up to now. We stored the keys, we've retrieved the other public keys, and we've encrypted the message with the public keys. Yes? So with an encrypted message, can you derive from that which public keys were used to encrypt it, or is it completely opaque? It's completely opaque. Were you going to, did I get the question wrong? Right, yeah, so all the public keys that were used, the associated private keys would be the ones that can decrypt it, but you can't tell from the message which public keys were used. Therefore, you can't imply which private keys. The only way you know is to try and decrypt it and see if it fails. Yeah, so another form of plausible deniability in that. All right, so now we want to decrypt the messages. We've got a database full of illegible stuff, and we want Bob to be able to see the message hi, because communication is hard. I think I'll probably need a more elaborate communication example. Hi is good. We'll do that. So remember this bit here we had before? We called the messages in that third line there, and we passed in the keys and the passphrase. If we look at what's going on in messages, we've again got this event loop style thing, the use effect. So what we're going to do is we're going to go to Superbase and we're going to select star from messages. Any concerns with that? So again, it is publicly accessible. So yes, you could determine how often messages were sent, but the sender and the message themselves are still encrypted. So there's nothing you can really glean in terms of who took part or what the conversation was, but you can see when conversation happened. I guess you could encrypt the timestamp as well. So we're going to grab those messages, we're going to set them into into state, we're going to remember what messages we have, and then down here we're just going to run through and iterate through those messages in order to display them to the user. But of course they're still encrypted, so when we go into the message component, which is called for every single message that's in there, we're going to get the message, the private key, and the passphrase. And then we're going to call decrypt message with private key. We're going to pass in the encrypted version of sender. We're going to pass in the private key and the passphrase. And then once that comes back, we're going to set the value to result. Now remember I said if you can't decrypt, it's just going to fail. So in that case, we're just going to set the sender to blank because we can't decrypt it. And then we're going to do the same with the message. And if that doesn't come through, then we're going to set that to blank. This is slightly abbreviated for the purposes of the slides because otherwise the text gets really tiny. In the working version, we'll have a look at it in a second. There's a little bit more to this. I actually have a value of, is this information censored? So I've got a censored true false in there. So if I can't decrypt the information, the app will actually say message cannot be decrypted or something to that effect. So you can actually provide information like there was a message, but you can't read it. Of course, you could choose, depending on how you write the application, to say, well, there was a message, but you can't read it, so we're not even going to show it to you. So you're not even aware of a previous conversation. You could go either way on that, depending on how you implement it. So let's have a look at the third party in the conversation again. This is the database preview that we saw before. Ben and Alice, I keep calling them Bob and Ben and Alice are chatting because that's my demo. Bob has absconded somewhere, I don't know. So this is the chat conversation before, and this is the chat conversation afterwards. And if we drill in and look at just one of those, this is what a PGP message looks like. So as you can tell, we're going to be using a lot more data. So if you want, I mean, obviously we've got gzip compression over HTTP calls and all of that, so it's not going to be that much worse, but it's still worse. So this is what a message looks like. And from this, you cannot deduce who sent it, who encrypted it, who can read it, what the content is. I don't even know if this one is the sender or the message. So the question now comes, and we've alluded to this a couple of times, how do you then add somebody to the conversation? Because if we look back at this one here, let's say Phil actually joins the chat. These messages here were only encrypted with mine and Alice's public keys. So we're the only ones who can decrypt it, nobody else can. So what happens if you want to add somebody to the conversation after messages have already been sent? Phil's absolutely right. I just give him my private key. No, I told you he was the bad one. I'm going to permanently change my slides to Phil. Adding somebody to the conversation. So this is what it currently looks like. This is Phil. Phil can't read the messages. This is the situation we were at the beginning, right? When we first went through how end-to-end encryption works. Once it got encrypted, Alice, Charlie, or Phil, or what was the other C? Carol. One of the people who weren't supposed to read the messages. I'm not going to call them attackers. Sometimes the C character is the attacker. But they're just third parties to the conversation who shouldn't be able to read it. But in this particular case, Phil's joined the chat. And we say, hi, Phil, or Charlie. and Phil can now see the message. That's cool, because Phil, Charlie, has generated a public-private key pair and shared the public key with Superbase in this case, or the server, and then next time a message gets sent, Alice or Bob, whoever sent the message, said, give me all the public keys, and that now included Phil's public key. So now Phil can read the message, but he can't read the first two messages. Can anybody suggest a way that we can solve that? Symmetric key encryption approach? Right. So if you had a common key for encrypting all the messages, then you could just encrypt that one key, and then every party to the conversation could decrypt that one key, and then use that for encrypting all of the messages. I would argue that you would probably actually want to over-engineer and have a symmetric encryption that rotates, which means you've also got to have a history of symmetric encryption. And you can use block data storage. I don't want to use the word blockchaining because it's not blockchain, but you can like encrypt one payload inside another so that you can then roll that back so that you can have certain messages with one key phrase, and then when somebody joins the conversation, you can change the phrase, the passphrase, but you can also allow them to see that passphrase, so you've then got optional, you can add somebody to the chat and say this person can see previous messages, and you can add somebody else and say this person can't see previous messages. You'd probably want to keep that kind of control. There's actually an easier way though. I mean, easier. One that doesn't require a technical change. Yes?
Okay. You might, I could be wrong, but could there, because Bob still has his private key and he can decrypt it, you could have like a mesh topology, and then Bob would generate a new key pair and then add Charlie in that way? Is that?
You're pretty close.
Okay.
When you started with, I'm probably wrong, you're not. You would use one of the existing members of the conversation, though. If Alice grabs one of the encrypted messages and then decrypts it using her public key, her private key, then grabs the three keys and re-encrypts it, sends that back to the server, as soon as that happens, Phil can read the message, or Charlie. And then similarly at the same time, because you've got multiple people connected all the time, right? You can just keep popping things off. Send me everything that has not been encrypted for Charlie yet. And meanwhile, Bob grabs another one of the messages, decrypts it, finds out, says, hey, Alice, re-encrypts it with the extra key as well now, adds that back onto the server, and now Charlie can read all the messages. So you don't really need to create new key pairs, but you're right in that you would use the graph of other members within the chat already to decrypt and then re-encrypt the information. Nice. That makes sense? Sweet. So, this is the fun part. This is not a malicious QR code. If it was, I wouldn't tell you. So, I'll leave that up for a bit in case you want to grab that. Basically, what that's going to load up is I've got this application running in Gitpod, and I've opened that up, so you should be able to get access. The first thing that you'll see is a login. Instead of logging in, because you don't have one yet, click on the sign up link. Or I think there's a login with Google as well, but email and password. I will be purging, that's the word I was looking for, all data out of my identity providers. It's not working? It's not working? Let's find out why it's not working. So it should, what can go wrong? Because my workspace closed. So I'll start this up again. But what I will be doing is if you do choose to log in with email and password, that will go into my demo identity provider space, but I'll purge that all afterwards. I promise not to spam you. Let's install Netlify CLI again. Shouldn't take too long, and hopefully, I think it usually keeps the same URL, so the same QR code should work. Anybody have any lift music? All right, let's go to start and Netlify dev. Not this one, that one, make public. All right, do you want to give that another try? Working? Yes. So you should see something like after you've logged in, something like this. Now, in fact, what you should probably actually see is something that just says, my clothes are falling off. Shimmy, shimmy. That's weird. It says what?
Mine says compile with.
Okay. Don't sign up with Google.
I signed in Google.
He signed up with Google. It works on my machine.
Mine's a Google Apps.
Okay. I'm just going to move this over so it's jangling against my... Sorry for this at home. It's going to be terrible for you. I have a necklace on, and it's probably bashing against that. There we go. That's better. So, I'm guessing, Phil, you saw two messages saying you cannot read this message. Stuart can't read Phil's. Although Stuart can read Phil's second message. Who's Bobby Tables? Excellent. If I had chocolate, I'd be throwing it at you right now. Ben can't type. Oh. Yeah, I got that one too. It means... can you actually... I can hear me touching the microphone, but I can't hear me through the speakers anymore. Is it loud enough? Okay, good. Yeah, so, working end-to-end app. Although, apparently I've got a bug to debug. What I would probably imagine is, who's the person that sent a message after I said hi all that can't be decrypted? No one. Spooky. Either that or nobody's admitting to it because they just want to freak me out. What I suspect might have happened is that maybe the call to save to Superbase didn't actually go through. There might have been a network error, in which case the public key isn't there. Or the call to receive the public keys isn't there. I don't know, something's gone wrong. Give it a try. Hey?
It doesn't even recognize that it's a password field, which is...
Well, no, it's a demo. Now you know my passphrase.
I'll just use yours.
Well, that's not going to work with your private key, though, is it?
But it will work for me.
It could also be a conference network issue. Nope, still can't be decrypted. Anyway. Whoever sent those messages, keep it to yourselves. You have unlocked an achievement I didn't even realize existed. Congratulations. All right. So, security considerations. Carry on chatting on the app if you want to. Security considerations we've already spoken about. In this particular case, we are retrieving information from Superbase. Nobody had used Superbase before. This is the information we're getting out, and if you sign up for a Superbase account for the first time and you haven't configured your security settings, you'll have this orange bar at the top of your screen that basically says you're allowing anonymous access to your table. But we've also already discussed that all the information is either a public key or ostensibly unencryptable without the private key, right? Ostensibly. Let's agree that there is no computer powerful enough ever in the world to reverse engineer this. So it should be safe, right? Maybe think of a reason why I'm asking this question in a very pointed manner, suggesting that there's something we've missed. Something about the ID? You could insert unlimited amount of data in your table. Yes, you could. There is a cost risk, I guess, in the fact that you could essentially do either denial of service attack on me or cause me to have to pay so much money because you've just uploaded 25 terabytes of data into one of my... But there's a worse one. Arguably, that's pretty bad, but there is a worse one. I'm allowed to read from the table, right? So that I can get all the messages out and the keys out. I can write to the table so I can create a new, modify, which basically means that nobody can read it, but you can also delete. I don't want somebody going through and say, just delete everything from the table. So in this particular case, because we're using Supabase, we would just change the security permission settings on this to say, by default, public are allowed to just read and insert, but they can't update and they can't delete. So, key takeaways from this. Have you had fun? That's the only takeaway, really. There are a few others. Securing private keys with a passphrase. I mentioned this at the beginning. You can create a private key without a passphrase. Don't. There are, I will admit, there are a small corner case number of examples where you might have a reason to do that. And that would possibly be in a scenario such as you're doing encryption that is only ever going to get touched by systems as opposed to humans within an environment that you control and trust fully. And in that case, you might want to just secure things more in transit than you normally would over HTTPS or TLS. If you want to send data and know that there's definitely no way you can decrypt it unless you have the private key, which you've specifically put onto these machines. You can tell where I'm going with this. Like, it's a very minute number of instances where I can think of where you would want to have a passphrase-less private key. Don't do it unless you've got a very good reason. If you do have a very good reason, tell me what it is, because I would like to add that to my repertoire of knowledge. Safe storage of private keys. This was a fun one, because there isn't really a way of doing this in a web context. There are certainly ways of making it more secure. And if you can't secure the private key fully, then hopefully you're securing the passphrase. If you're not securing either of those, then, I mean, you're buggered, basically. But there are other things you can put in place to mitigate this. Safe handling of passphrases, same as the last, only a different piece of data. Access control to encrypted data at rest. We looked at how we secured Supabase a little more to make sure that only what we anticipated public actions to do. The other thing I like, by the way, about having public write access to that database is, yes, you can write dirty data into it, and ostensibly it's not really going to create any problems because all the app's going to do is try and decrypt it and it'll fail and it'll say, could not decrypt this message. But the other thing I like about it is it adds even more onto that plausible deniability, because you could secure it using the JSON Web Token that came from the identity provider and configure the database to say, accept any access tokens that are issued by this identity provider. But now the database has logs of who wrote which piece of data. So I don't want that. So more plausible deniability on top. We've gone through how to re-encrypt data and why we would want to do that to provide information to people who've joined a conversation later on. And again, I want to emphasize, don't roll your own crypto. It's not worth it. Unless you are actually super mathematical and this is your job and you write crypto stuff all day, absolutely, go for it. It's your job. I'm not going to stop you. I would also like to thank you very much for creating the tools that we use so we don't get ourselves into trouble. If you don't know how to write a cryptographic algorithm, don't. Swiss cheese model, I've mentioned a couple of times. We're adding lots of layers in here to try and keep us as secure as possible. The next slice of cheese would be user backend. And most importantly, drunk people with fire extinguishers are largely unhelpful in times of peril. I learned that at the age of 40 as well. I'll tell you more about that afterwards during drinks, because I believe in the next 15 minutes or so, we're going to be plied with alcohol, I imagine. So I'd like to thank you very much for your time. I hope it's been enjoyable. I've been Ben. There's a QR code and the URL to the actual workshop if you want to do it. It is a pace yourself, do it yourself workshop. That's the option there. And together with what we've spoken about today, that fills in the gaps of what I would normally be talking about during the workshop. So feel free to give it a try. Message me again, Ben Dechrai on Twitter. My DMs are open. Thank you for your time. And of course, I'm happy to take any more questions if there are any.
Does the ciphertext length vary as a function of the number of public keys?
Say again?
Does the ciphertext length vary as a function of the number of public keys that it is signed with?
That's a really good question. I would imagine it would.
I'm just thinking, right, if you had a situation where you wanted to determine the size of a group and you're a third-party actor like a nation state, and the thing's signed with 5 keys versus 20 keys versus 1,000 keys to determine the size of the problem you're dealing with.
That, so just to fill in for the people at home, gentleman in the back was saying you don't know the length of the message. So the question is, if you look at the length of the actual encrypted data, can you infer anything from that in terms of the group size? And the commentary was, if you have a really small message encrypted for many people, it might look the same size as a very long message encrypted for a few people. I think you also mentioned padding, and I think there is a padding mechanism in that so that it's harder to guess. Now, if you knew that an average length of a message, let's say, for example, you were using this to encrypt SMS, I don't know why you would, or tweets, and you know that an average length of a message is 89 characters, because it's up to 140, but the average is usually 89. You could probably infer from that, but probably only in blocks because of that padding that goes in there as well. So I guess you could, if that was a great concern to you, you could also implement a similar aspect to seeding a hash. You could add a whole lot of variable data at the beginning, and in your application, you can say ignore everything up to the null character, and then the rest of it is message, and you could have a variable length. You could add your own variable length padding to the message to add even more noise, make it harder for people to guess what's going on.
Or I'd also wonder, perhaps you split it up into frames. So, one single message only has up to X characters, and you split up over multiple messages.
Totally, you could definitely do that. Lots of different ways you could add on to this for even more security. I like the frames idea. Cool. All right, if there's nobody else, I'm going to stick around anyway for the next couple of minutes, but if there's nobody else, go outside, have fun, and I'll see you at the party. And don't forget to come back, it's room 1, right? Room 1 for the karaoke. There is conflicting information. It's one of these rooms for the karaoke, but don't miss it. It's going to be amazing.